Hi all, and thanks for listening in. I'm Kevin Wallin, and today I'll be talking about a new program that we started working on at the U of A this year called Measurements of Shear Induced Pore Pressures in Over-Consolidated Clays and Weak Argillaceous Rock and the Impact on Strength. I'd like to start off by showing this figure about the shear stress and shear strain patterns of two elements A and B, within a strain weakening material. This particular figure depicts shearing a deposit of quick clay. What we see is that as rapid deviatoric loading occurs along the shear band of this landslide, excess pore water pressure builds up due to the contraction of the material in the shear band. As the shear band progresses upslope in the strain weakening material, the shear strength of the material decreases from either a pre-peak or peak, as with element B here, to either a working or residual strength due to in large part to increases in pore pressures as seen at element A. These excess pore pressures significantly decrease the strength of this material throughout this shearing process. Now, what if I told you that something not completely dissimilar could potentially be occurring in heavily overconsolidated clay or weak argillaceous rocks like shales? You might think I'm out to lunch, but hear me out. Fundamental behavioral models for saturated overconsolidated soils have typically been derived using conventional triaxial stress paths. There are two main shortcomings to this test. The first is that they only utilize a constant normal load boundary condition. A constant normal load condition in nature is comparable to a block that is sliding along a slope where dilation can occur at the shear boundary between the block and the slope. Around underground excavations or along the shear zone of very large landslides, however, the far-field ground tends to act as a spring at the location where strain is developing, creating a constant normal stiffness condition. This boundary condition causes the dilative contractive response of the strained soil to behave according to Hooke's law, where the spring stiffness is equivalent to the rock mass stiffness. Restriction of dilation then creates the potential for shear-induced pore pressures to develop. The second shortcoming of traditional triaxial tests is that they only capture external pore pressure measurements. The extremely low permeability of overconsolidated clays and clay shales mean that these external measurements are likely not capturing the true internal pore pressure response of the material along the shear band. The hypothesis of shear-induced pore pressures is supported by field readings. These even include measurements taken at Ripley landslide site, where increases in pore pressures were observed on the failure surface during slip events. This work is of particular interest to the railway infrastructure of Canada, as most river valley systems in Western and Central Canada are either underlain by overconsolidated clay soils, like those found at the Ripley landslide site, or weak shales like those that can be found within the Assiniboine and Qu'Appelle River Valley systems. Our current understanding of heavily overconsolidated clay or shales is that they have a dilative response, which leads to a decrease in pore pressure during shearing. This decrease in pore pressure would then lead to an increase in shear strength. Our work hypothesizes that this fundamental understanding may be overestimating the capacity of these slopes to short-term undrained shearing events when strain-controlled boundary conditions exist. Proving or disproving the presence of shear-induced pore pressures will help us more accurately capture what is occurring along the shear zone of landslides, in turn helping us to more efficiently protect and transport goods safely across rail infrastructure. Our overarching objective for this program can be stated as wanting to advance the understanding of coupled geomechanical processes in heavily overconsolidated clays and weak argillaceous rocks. If we break this down into less lofty goals, the objectives include wanting to observe the presence of what we are terming shear-induced pore pressures in a lab setting in three types of soils: a man-made heavily overconsolidated sample, in a weak argillaceous rock called opalinous clay, and in the very weak Pierre shale collected from the Assiniboine River Valley. To quantify the effects of shear-induced pore pressures on the pre-peak material strength response of this class of material, both through lab testing and field data analysis, and to quantify any scale effects that may be occurring when comparing the field and lab data. So in June of 2019, myself, with the help of CN and mobile augers, completed a drilling investigation at mile 184.4 site within the Assiniboine River Valley. At this time, we completed 2 boreholes to about 35 meters, collected samples in one of the boreholes, and installed sloping clinometers and vibrating wire piezometers in both holes. A triple tube mud rotary coring system was used, where plastic liners were placed inside of the core barrels instead of traditional metal slips. Samples were collected directly into the liners, sealed using wax, capped, wrapped in plastic wrap, and then placed in wooden core boxes for transportation. The drilling technique was specifically chosen as marine shales experience rapid degradations in sample quality if not properly preserved. This also allowed us to preserve the samples for a longer period to be able to conduct X-ray scans and lab testing. Through this work, I completed my Master's of Engineering degree and produced a conference paper and presentation that was included as part of GeoVirtual 2020 proceedings. This work focused on assessing the shear zone of the landslide at the mile 184.4 site using X-ray scans of core samples coupled with instrument readings. The main conclusions that were found were X-ray CT is an underutilized technique for characterization of core samples for slope instability projects. The increasing availability and affordability of X-ray CT devices enhances the ability of geotechnical engineers to characterize and understand dynamic processes in soil and rock. X-ray CT is a valuable tool to observe and analyze density variations in soil deposits. That X-ray CT is a relatively cost-effective and expedient way in visualizing macro features in core samples. That is particularly well suited to soft sediment structures or clay shales, which can experience rapid degradation in sample quality if not properly preserved. If anyone would be interested in reading the paper, just let me know and I can send you a copy. So if we jump back into this current project, this work stems from previous collaborations between NAGRA and the U of A, and primarily based out of Mont Underground Rock Laboratory, which is an international research consortium working to understand whether radioactive waste can be stored safely in opalinaceous clay, and is one of only 3 major URLs in the world examining the fundamental behaviors of in situ shale deposits. Mine-by or tunneling experiments have been conducted at Mont while gathering stress, movement, and pore pressure readings. This includes the MB experiment, which was advanced in 2008, and more recently the MBA and GCA, which will be the focus of the field portion of this research program. During these tunnel advances, pore pressure responses that don't fit the typical expected behavior for heavily overconsolidated clay or weak argillaceous rock was observed. As an example, we can see here that the pore pressure response of the piezometers installed for the Mine-by advance in 2008 show a coupled hydromechanical response beginning to occur as far out as 10 meters from the tunnel face. These spikes in pore pressures that we see here reached upwards of 2 MPa and led to the onset of yielding of the surrounding material to occur at relatively small strains when we compare it to the laboratory data gathered for the site. Based on the current fundamental understanding, we would expect there to be a slight contraction of the ground leading to a small increase in pore pressures, which would then be followed by a dilatant response and a decrease in pore pressure. This decrease in pore pressure would then lead to an increase of the material strength, but this was not the case at the site. A shortcoming of the MB experiment, however, was the location of the piezometers relative to the tunnel face. The piezometers were installed at a fixed radial distance from the tunnel wall. This approach effectively captured the pore pressure responses occurring within the affected radial zone, but failed to capture the displacement and pore pressure response occurring in front of the tunnel face. The more recent MBA and GCA experiments fixed this shortcoming by installing sensors in front of the tunnel. Here we see the instrumentation that was installed through the CSD and SW niches for the MBA experiment. The MBA tunnel was then excavated towards the instrumentation, or upwards in the image on the left. Sacrificial pressure sensors were installed directly in the drill path to truly capture what was occurring in front of the tunnel face during the drive. These 2 experiments will be the focus of this field portion of this work. These increases in pore pressures can potentially be explained by Terzaghi's effective strength relationship in 2 dimensions, or taken one step further and analyzed in 3-dimensional space using Bayet's poroelasticity framework. Terzaghi's relation shown here is generally used to define frictional resistance for bedding plane stiffness. This states that variations in pore pressures can be caused by volume changes, so dilatancy versus contraction, and that the volume change of shear planes, like those that develop during landslides, or of bedding planes, like those seen at Mont in the opalinaceous clay, are further associated with the stiffness of the stress-strain response of that specific layer or zone. It is already well understood that the pore pressure in heavily overconsolidated clays or shales will respond differently when testing occurs parallel or perpendicular to the bedding plane direction. However, there hasn't been definitive evidence proving or disproving the presence of shear-induced pore pressures in a lab setting along either shear bands or along bedding planes, as all testing is currently completed using global pore pressure measurements. Therefore, this research program is really focused on reassessing the fundamental behavior of this class of material by advancing current lab testing methods to support the findings of the field data seen at Mont. This research is specifically focused on gathering internal pore pressure measurements in the lab rather than relying on global measurements. The program that we've envisioned can be broken down into 3 stages with various tasks. The first stage will revolve around a laboratory testing program consisting of triaxial testing, direct shear testing, and finally an analysis of the results. The second stage revolves around gathering, synthesizing, and analyzing the existing instrumentation data collected at Mont during mine-by-type experiments. The final stage will consist of comparing our findings from the field and lab program, examining if shear-induced pore pressures do in fact exist, and how this might affect the behavior of saturated overconsolidated clays or clay shales. To gather internal pore pressure measurements, we plan to seal microfiber optical sensors into the samples in both triaxial and direct shear cells. The fiber optical sensors we are using are developed in Canada by a company called OpSense. These sensors were originally developed for the medical industry to monitor pressures within the human heart. These sensors are diaphragm displacement sensors that are based on microelectromechanical system technology. We tested the functionality of the sensors in 2019 and subsequently ordered some. The operating range of the sensors is about 1 MPa and has an outer diameter of about 0.3 of a millimeter. For our purposes, a protective casing was placed around the sensors, thus the proposed working diameter is actually about 0.6 of a millimeters. I've actually included a picture here of one of the sensors that we have against a pen for scale. The triaxial program will consist of gathering internal pore pressure measurements using a conventional triaxial test with microfiber optic sensors embedded into the sample. The purpose of this task is to validate the internal pore pressure readings collected using microfiber optic sensors, to develop a procedure for sample saturation and consolidation during direct shear testing, and to further investigate the anisotropic pore pressure response of overconsolidated bedded materials using internal pore water pressure measurements. The direct shear testing consists of modifying an existing servo-controlled direct shear apparatus at the U of A. The purpose of this task is to apply a constant normal stiffness boundary condition to the samples while collecting internal pore pressure measurements. To further investigate the difference of internal pressure measurements using a CNL or a CNS boundary condition. But the main goal of this task is to observe and quantify the presence of shear-induced pore pressures under a CNS boundary condition or constant normal stiffness that is similar to that seen during the mine-by experiments at Mont. The existing servo-controlled apparatus that we have can be programmed based on vertical or horizontal force and displacement. This also allows us to be able to complete unload and reload cycles on our samples. These unload-reload cycles are of interest because the accepted industry practice at this time is that the stiffness of a shear plane is assumed to be constant throughout the shearing process. The programmability of our device affords us the opportunity to better quantify if there's a change in strength or if there's a change in stiffness of the material throughout the shearing process. As mentioned previously, we will be synthesizing and analyzing the field data from the MBA and GCA experiments at Mont. We will then compare the results from the field program to our direct shear testing results. The direct shear tests will be the first to truly mimic the strain-controlled boundary conditions that exist at the tunnel face during the mine-by experiments while capturing internal pore pressure measurements. Our hope is that the internal pore pressure measurements show spikes similar to those seen during the tunnel advancement. The purpose of this task is relatively self-explanatory. We hope to observe a direct link between the pore pressure response in the field when compared to the lab setting. The things that we hope to quantify through this process include the discrepancies between the strain to failure observed in situ versus in a lab setting. Failure has generally occurred at small strains in situ, leading to a much smaller yield values than what has been predicted through traditional lab tests. Also, because the direct shear test will be completed under the same boundary condition as in situ, We hope to quantify any scale effects that may be in play going from a small lab sample up to a large tunnel experiment. So the one-year plan revolves around constructing the lab equipment necessary for testing various samples in a lab setting, and finally beginning the assessment of in situ experiments. The triaxial cell is currently being constructed, and the design of the direct shear device is completed, and it will be constructed once the triaxial cell is completed. We do expect there to be significant difficulties with refining the lab testing setup and ensuring that the internal pore pressure measurements are valid. This will require an iterative trial and error approach to resolve any issues encountered throughout the lab testing program. Initial trials will be completed on man-made samples, during which time we will be refining the sample handling, preparation, and testing procedures. Our hope is to have all the kinks worked out by April of 2021 to hopefully complete all lab tests by the end of the year. Gathering of information and the analysis of the field experiments conducted at Mont will overlap throughout the lab program, but is planned to be completed early 2022. So there are a number of outcomes that could result from this work. This program represents the first attempt to gather internal pore pressure measurements during direct shear testing, and is also one of the first to attempt this within a triaxial cell. This program is also highly focused on the proper implementation of boundary conditions during lab testing. Traditional triaxial tests that implement stress-controlled boundary conditions are applicable to many geotechnical applications, however, may fail to capture all the variables of larger problems such as tunneling projects, nuclear waste repositories, tailing structures, and large landslides, just to name a few. The preliminary evaluation of field data from Mont appears to show something that resembles shear-induced pore pressures. One of our major outcomes from this program will be to either prove or disprove their shear-induced pore pressures as a whole. Regardless on this outcome, however, the work we do will help to advance the current geomechanical understanding of over-consolidated clays and shales, with a specific focus on pre-peak strength internal pore pressure behavior. This information can then be further applied to understanding the stress-strain behavior of this material, or things like damage initiation or crack propagation within deposits, for example. Finally, if shear-induced pore pressures are shown to exist, this would change how geotechnical engineers assess undrained shear strength in this class of material, specifically when strain-controlled boundary conditions exist. So we'd be changing the fundamental model for this type of material. So that's it, but I'd like to thank and acknowledge our industry sponsors, NAGRA and NWMO, for providing funding and in-kind support. I'd specifically like to thank Silvio Giger with NAGRA and Hossein Kassani and Monique Hobbs with NWMO for their time and support so far. I'd like to acknowledge the support of the Natural Science and Engineering Research Council of Canada. I'd also like to thank Alessio Ferrari with EPFL for providing technical support, and of course the members of the Supervisory Committee and support team at the U of A, specifically Vivian Zhang, Nathan Deisman, Jakob Brandl, and Lucas Dirksen. Thanks all.